Understanding the memory access cost on cached architectures is hard. We present with Haystack an analytical cache model that provides programmers with exact cache miss information. Haystack counts cache misses for every memory access of a program, assuming full associativity and a least recently used replacement policy. The stack distance is the core of our analysis. It counts the number of distinct memory accesses since the last access of the same memory location. All memory accesses with a stack distance larger than the cache size are misses. Symbolic counting techniques allow us to count hits and misses without simulating the full program execution. For a wide range of compute kernels, we provide results within seconds and clearly outperform alternative approaches. At the same time, the results are accurate compared to performance counter measurements.
Several applications are built around trees that are traversed by multiple tree traversals. Render trees, abstract syntax trees in compilers, and KD trees in scientific computations are examples of such applications. In those applications, multiple traversals traverse a tree to perform some computation. It's desirable to fuse and combine those traversals together if possible and perform less traversals. Such fusion reduces the traversing overhead and achieves better locality. But it's not always possible to fuse those traversals. Furthermore, manually fusing traversals is not trivial, prone to errors, and less modular. We introduced Grafter, a framework that automatically fuses tree traversals that are written in a general programming language. Grafter is sound, automatic, general, performs fine-grained fusion, and supports heterogeneous trees. We showed that Grafter is able to reduce cache misses by up to 80% and runtime by up to 60%. If you want to know more about Grafter, please come and attend my talk.
We present a way to check for termination dynamically. What's remarkable about a dynamic termination checker is that it can check programs that only terminate on specific inputs, such as interpreters of Turing-complete languages on specific programs. Our dynamic checker is able to check for the termination of programs such as a scheme interpreter running Factorial, Ackermann, and merge sort. Being able to check for termination at runtime creates new use cases. For example, we can integrate termination checking into an existing high-order contract system, allowing contracts to enforce total correctness at runtime. Termination contracts also open the door for sound enforcement of termination in gradually typed languages, where the static type system can express total functions. To find out how we do this, come to our talk.